Hello everyone, I hope you can see me. First of all, I think before we start, okay, we will just do the usual things, okay? Just write down in the comment uh, on your student ID, okay, so that I know who have actually viewed this, and I will take note, okay, so that everyone have the opportunity to actually check these lectures, right? So during the sessions, if you have any questions, okay, just post it in the comment box. Then I will try to attend it, okay, as much as possible, right? Okay, so I guess we should start. Okay. I have posted this notes, okay, previously, okay, in the smart tree, okay. If you have noticed, there is this notes there for I think 2 or 3 weeks there, right? But then since we are allowed to continue with our online sessions, okay, just to prepare to the coming continuations of the semester, okay, in 9th of June, all right? So we will start early, okay, so that we have a longer time, okay, in between lectures, right? So that especially for those who have poor internet connections and other problem, okay, they can always do it, okay, in a longer time, right? That's why we start this semester, even though officially it's on 9th of June, okay, but we take into the account that we have to make it longer, so we start earlier, right? So before we go into the content of these lectures, okay, I just want to re-highlight again some modifications, okay, due to the online sessions that we will use, okay, throughout the remaining of this semester, okay. So since we will purely depends on online, okay, for those who cannot do it online, okay, do not forget to inform me through WhatsApp, okay, as if you can WhatsApp, all right? So hopefully you just send a message or through email, okay, to notify what is your problem, so that we can do what the necessary things, okay. So we can see that this is our course objective. We have 5 course objective, okay. The course objective will remain there, okay, but the way we try to assess it will be different now, right? Since this online courses to be conducted on everything through online, so the tutorial become an important element now, right? Previously you are not required to submit, okay, but now we will take some marks from there, right? So I hope you can try it and discuss, okay. You can always discuss in the Google Classroom, okay, with your friends. It's okay, okay, as long as you submit, right? So this is the way we will do it, okay. So we will have 4 items: tutorial, quiz, test, and eportfolio, all right. So this is the changes in the weightage, okay. Previously we have the 40% final exams, right? But now we have totally removed the final exam, and we will do it as a continuous assessment, right? So we will assess through your tests, okay, for maybe 1 or 2 chapters, okay. We will have a test, okay, then also quizzes, okay. Those quizzes are basically the theoretical questions, and then we have the e-portfolio to do as your assignment, right? So this e-portfolio actually is just maybe a platform or website, okay. You can just create a blog, okay, or YouTube or whatever it is, okay, as long as you can show that your work, okay, your project, okay. So this kind of task, okay, I will give you from time to time, okay, so that you just add in to uh, your blog or whatever it is, okay. And then it will become your portfolio, means at the end you can always show to someone that you have this knowledge, okay, you have this ability to do this certain work or task, right? So that is your assignment. Then again, tutorial, okay, you just have to go through back your previous lecture. There is tutorial questions at the back, okay. You just try it, and then you can scan it or just take capture of the pictures, okay, and send it to me. If you want to keep a proper record, then you may want to type it, okay, it's up to you, okay, as long as you submit, right? So here is our course plan. There is not much changes in our course plan, okay. We have covered, luckily we have covered most of the things, okay. We have covered up to the prismatic bar and then beam equations before we have this so-called MCO, all right? So we have started our beam equations classes on 16th of March, then followed by the plane stress, plane strains conditions, right? So today is the continuations of the lecture, okay, on the plane stress and plane strain, okay. In the previous lecture, we talked about the constant strain triangle elements, okay, CST, and today we will focus more on the Q4, okay, the quadrilateral elements, okay. So the only additions thing that I have put in is the isoparametric formulations, okay, isoparametric formations, just an introduction to all of you, okay, what is that, okay, and before we move on to other things. So we can see that this is just a tentative time, okay. We will try to have our online streaming, okay, on this date, okay. So it will be about 2 to 3 weeks gap in between them, okay, so that you have more time to go through them, all right. So the online video streamings will be short, okay, maybe 1 hour, okay, but you need to do others so-called readings on your own, right? So we can see that previous, as I mentioned, so we will move into this chapter, okay, and it's related to the rectangular plane elements, okay, or we call it as Q4, okay, quadrilaterals with 4 corner nodes, okay. So in this element itself, as we can see, there is only 4 nodes. Therefore, there is no midpoint or mid nodes in between the edges, right? So the advantages of using this Q4 over the triangular elements is the ease of data input, okay. You can easily enter the coordinate and so on. Then is simpler interpretations of output stress, okay, easier to calculate, okay. But then there's disadvantages of the Q4, which they poorly approximate the real boundary condition edges, okay, especially when there is a corner, okay. So if we use a rectangular type of elements, you may have difficulty to actually approximate the curve part, right? So the steps to derive for this Q4 are very similar, okay. We will just go through as quick as possible. So first part, the step 1, you will have to select the element type, okay. So here we tend to try to see what is how to derive for the Q4, okay. So the Q4 actually basically is just a rectangular elements with 4 nodes, okay. So you have seen the nodes 1, 2, 3, 4 being labeled in the clockwise directions, okay. So the base and the height will be 2b as given, and there is a unknown nodal displacement, okay. So this unknown nodal displacement, as we can see, there is u1 and v1. u1 and v1 represent the displacement along the x directions and the y direction for each for node 1, okay. So you have node 1, node 2, node 3, node 4. So every single node there is 2 degree of freedom. So there will be 8 unknowns for the nodal displacement, right? Okay. So then we will start to select the displacement functions. Okay. Since we have 8 degree of freedoms or unknowns, then we will have to create the so-called displacement functions, okay, with 8 constant, okay. So we have a1 until a8, all right. So for u, we have the u linear displacement function, we have a1 plus a2x plus A3Y plus A4XY. Okay, similar for the V, right? So how we can do this? Okay, we just go through the previous lecture. Okay, we have tried to formulate the shape functions by using this. Okay, so what we can do, we will form them into a matrix. Okay, so we just form into A1, A2, A3, A4 until A8. Okay, to form into matrix in order for us to eliminate the constant A. All right, so here you can form into the matrix 1 x y x y. Okay, to multiply by the A1, A2, A3, A4 in order for us to get the U linear displacement functions. Okay, similar for the V displacement function, we have this matrix. Okay, so if we want to really solve them, okay, to solve for this A1 until A8, we need 8 simultaneous equations. So what we do, we just write them or expand them actually into the node. All right, so since we have 4 nodes, so you have 1, 2, 3, 4. Okay, so and then we just rewrite the equations for each of the node. Okay, and this corresponding to this, right? So therefore, from this this function itself, then this U x1 y1 represent u1. Okay, this u x2 y2 represent u2. Okay, so what we can do is that you can form the simultaneous equation. So you have u1 equals to a1 plus a2x plus a3y plus a4x1 y1. Okay, so that is how we can form the equations, and we can run through the 8 equations. Okay, so this matrices is just to help you to run in the program. Okay, so that they can do the calculations and solve it on their own. All right, so by doing that, we have 8 equations, solve them simultaneously, then you can solve for the A1 until A8. Okay, at the same time, we can try to eliminate to form this U and V equations. Okay, so eventually when we remove all this, we will obtain this linear displacement for U and also for V. All right, as given as in the equation 6.6.3. Okay, so now from that equation itself, if we try to locate this kind of form, okay, we will see that the shape functions appear. Okay, the n appear. Okay, from the previous equations. So this shape function itself we can write as n1, n2, n3, and n4. Okay, which represent the shape function for at the node 1, node 2, node 3, and node 4 itself. Okay, as given, right? So graphically, okay, for us to visualize, okay, then the shape functions at node number 1, okay, node number 1, then we can see that the weightage or the values at node number 1 will be what equals to 1. Okay, for both x directions as well as y directions. Okay, so if we want to directly, okay, check whether the shape functions being derived is correct or not, we can have a quick check actually. Okay, we can form the linear functions for this part, right? So this represent how the weightage actually change. Okay, shifting from node 1 to node 2, right? So if we form the linear equations, okay, this is just y equals to mx plus c. So you have y equals to mx plus c. We can get the n1 will be equals to minus x plus b divided by 2b. Okay, to represent this particular part. Similar for the y L1y itself, they have a similar equation. So if we combine them together to obtain the shape functions, okay, for node number 1, we just multiply them for the x and y combinations. We will have these equations. Okay, and if you compare this with our previously derived shape functions, they are equals, right? So this is the ideas behind the shape functions, right? So all these shape functions will have the similar requirements, all right? So once we have the shape functions, now we can rewrite them in a matrix form, okay? In this course, okay, many times we rewrite them in the matrix form so that they can systematically compute, okay? Just like what you have learned in the numerical methods, okay? They can computationally calculate, okay? You can do this using MATLAB, Scilab, or even Excel, okay? So if you don't have those tools, you can always depend on Excel to run on your code, right? Or to run on your calculations, okay? Excel have a built-in functions to solve for metrics, right? So you just Google from there, you can solve them, right? But then there is some limitations on the number of, or the size of the metrics, okay? So you have to be aware of that, all right? So once we have obtained that, now we move to the strain displacement and the stress-strain relationships, okay? For this part, it's very similar, okay? We already have our defined relationship for the strain in X, strain in Y, given as such, okay? As well as the twisting, okay, part of the strain, okay? So it's given by this, all right? So here we can, what we do, we just do the partial differentiations, okay, respect to our equations previously, okay. So since we already know the A1, A2, A3, and A4, assuming that you already performed the symmetry equations previously, okay, you already know that, so we can actually calculate, okay, accordingly, right? So if we take derivations with respect to X, so we will obtain this equation. With respect to Y, we will obtain this equation, and so on, okay? And then all this strain, okay, there are the relations they are related to the nodal displacement, okay? So again, we try to rewrite in this form, okay? And we identify or separate them away with the displacement, the unknown parameters, okay? So we notice that there is this part B matrix, okay? So this B matrix is given as such, right? So you can try that on your own, right? Similar to the stress, once we know the strain, then we can always calculate for the stress, okay? Where this stress is just multiplications of functions or metrics, okay, depending on your problem. If it is a plane stress problem, then we use equation 6.1.8, okay? Then if it is a plane strain problem, then we use 6.1.10, right? As seen, okay? So what we do when we multiply them together, we will obtain the stress matrix, okay? So all these are computationally intense, all right? So you can try it on your hand, all right? But then later on, computer will do better, okay? Then after we obtain that, we will start to derive the elements stiffness matrix and equations, okay? So this part, we will depend on this stiffness matrix defined by the integral, okay? A double integral, all right? Given in previous lecture, okay? So here we rewrite as 6.6.10, okay? You can always see back the previous equations number, right? So double integrations, when we integrate them, we will obtain what we want, okay? The elements, the K, the stiffness metric itself, right? So these double integrations, again, here is mathematically represented, okay? But then in the computer or in the software itself, they will run the numerical integrations, okay? They will do the numerical integrations. That's why it comes in with the methods like Newton Cotes, okay, Cotes, or maybe Gauss methods, all right? So all these are are common methods that's used in the software itself. All right. So different methods will have their advantages, disadvantages. All right. But then most of the software now, they tend to move use the Gauss quadrilaterals methods, okay, to solve for the integrations, right? So that part, numerical part on how to solve them is not part of this subject, okay? It's just a knowledge, okay, on how. If you are interested, you can always check that, okay, on your own, right? So once we have obtained this element stiffness matrix, okay, the rest will be similar to what we need to do. All right, we can form the element force matrix, okay, as well as this is the unknown, okay, displacement, okay. So these unknowns we have already obtained previously, right? Okay, remember we have come up with the equations previously, and we should able to solve for that. Okay, once we have solved for that, then we can calculate what are the forces and how they are interact. Okay, they may be interact back. Okay, that's why there is the so-called looping, or there is a interdependence. Okay, that's whenever a calculations occurs, they will do calculate and then check. Okay, so this part may become part of the checking part, okay, to ensure that they are matching. Okay, once they are matched, means they have converged, right? So every calculations, every single elements they will run, okay, again but again on their own, okay, to ensure that at the end all the metrics or the equations are actually matched with the force given, right? They have to check that. That's why there is this convergence part coming in, right? So now we will see the numerical comparisons of the CST and the Q4 elements, okay, as quick comparisons from the book logans, all right? So we can see that we have this this deflections problem, okay? Once fixed N, okay, with a cantilever beam, right? So with a force 4,000 Newton, okay, and the length as given, right? So what they try to do, they compare with using Q4 elements, okay, but then using 2 row, okay. 2 row means they have only 2 boxes, okay, 2 rows, okay. So this is their elements, all right, and so on, okay. Then there's 4 rows and 8 rows. So this shows 8 rows, okay. Whereas for the CST, they compare with 2 row, 4 rows, and so on. So we can see that from this table itself, and we compare with the theoretical beam theory, okay, we've noticed that Q4 have actually reached that particular values very fast, okay, even though it's using 2 rows, okay. But then in the CST itself, we see this problem, okay. The displacement is not large enough, okay. There is a very, it seems like there is a very stiff members, okay, acting on it, all right. So when we further increase the number of row, okay, then the result improve, right? So for the eportfolio, as I've mentioned previously, okay, what you need to do now is you try to simulate these conditions again, okay, but then since this is using 1 meter, okay, you may have a lot of nodes, right? You can see the number of nodes is large, okay. So what I recommend you is that you define your own conditions. It can be half meter, 20, 0.2 meter, up to you, okay, as long as you are good with it, okay. Form your own problem, okay, then you try to use the same problem, cantilever beam, okay, apply your force, okay, and then you check, okay, what is the displacement, okay, and the stress, okay, corresponding to the theory, all right. So I would like you to do for only four type of conditions. The first one, the Q4 with 2 row, okay, then the CST with 2 row again, but then this dash one is this way of meshing, okay. You can see that the meshing directions load is here, it's pointing with an arrow like this, okay? The CST-2, I wish to see the opposite directions, okay? The opposite directions. And the third mesh way, okay, in this form, all right? You can do it using whatever methods you think is good, okay? You can use Lisa, okay? If you don't have Lisa, you can use Excel, you can use MATLAB or whatever it is, okay? As long as you can show it, all right? And then what you need to do, you just put them in the PowerPoint presentations, okay? Document them properly, all right? So this we have discussed, all right? The displacement result is, we can see that the CST model produce the model itself, okay? And it converge slowly, okay, to the classical beam, okay? This is partly because of the characteristics of the CST itself. And when we deal with the bending problem, the stress actually linearly dependent or varies with the depth, okay? That's why whenever the number of row along the depth increase, the results getting better, right? So the Q4 again is predict more accurate deflection behavior than the CST, and the number of rows increase to 4 and then 8, okay? Increasing more accurate, okay? So this is what happened, right? So we can see that the two-node element itself, all right, the two-node element itself given in the theory is, okay, when you are not concerned, okay, with the stress concentration, then yes, you can apply this so-called beam elements, okay? You just use beam element, right? Instead of using the CST or the Q4, right? So these beam elements will give you a good satisfied results, okay? If when you are not concerned with the stress concentrations, okay? So this is the general ideas of it, right? So if you note that a single row Q4 with their linear is not recommended, okay? Single row itself, okay, is not recommended for Q4 because of the behavior of the linearly decreasing or changing stress, okay? There is a stress gradient through the depth of the beam, okay? That's why, if possible, 2 or more, right? This is where when we deal or when we model the final elements, okay, the directions of the force is important, okay? When it will helps you to decide the number of the meshing, okay, along that particular directions, okay? So this is critical informations for you, okay, when you're doing the modeling, all right? So here there is one famous or maybe popular keywords, okay? Shear locking, okay? Shear locking is more, shear lock itself, okay, is more commonly known, all right? Or in other words, they may call it parasitic shears. What happened is that as we can see, what happened in the previous, we can see that the CST itself produce poor results because you can see when this is a element row, the displacement is very small, means the beam itself is very stiff, right? Okay, why this happens? Okay, we call this phenomena as a shear locking. Okay, in this shear locking itself, the CST have a forced shear stress occurs inside, okay, that try to absorb those energy. Okay, so whenever they absorb this so-called energy, means the energy that's supposed to go for bending is now lost, right? So we call this phenomena as a shear locking, okay, or other words, parasitic shear, okay? So what we can do in problems where plane strain conditions exist, okay, and the Poisson ratios approaching 0.5, the maximum value of the Poisson ratio, 0.5, okay, mesh can actually lock, okay? This is where it's conformed to log, all right? Okay, so means the elements or the mesh will not able to deform anymore, all right? So a simple illustrations, this is a beam, okay? When we apply a bending moment itself, in the actual case, we expect the bending, right? But what happened in the shear locking is that the displacement of the knot shift but not bend down, okay? That is what we call shear locking, okay? And this will result to the error in the stress itself, okay? Because of no changes in terms of displacement throughout others knot, okay, along this member, okay? So as we can see, the shear stress itself is dependent on the displacements, okay? So first thing, whenever someone try to analyze the FEA results, okay, the experts, they will always look at the displacement result first, okay, even though the intention is to check the stress, okay, because the displacement give us a visual, okay, or more a visual kind of image, visual type of effect, okay, that we can imagine, okay. If some forces acting, you can predict, okay, visually, okay, in your mind or from your experience, how it changed, okay. That give us a very important informations, okay, before we check whether the stress, how the stress is actually change, okay, corresponding to the displacement itself, okay. So first thing, check the displacements first, okay, whether it's correctly represent the actual conditions or not, okay. Otherwise, whatever stress results that you get may not be correct or true to the real situations, okay. In order to mitigate all these problems, yes, we can always use a finer mesh, okay, depending on the computational capability of your computer, okay. But we can always refine our mesh, okay, to allow more bending to occur, right? So here again, part of your eportfolio, right? You can make some presentations in the video form, okay, to explain what is hourglass effect, okay? Just Google it, what is hourglass effect and how the hourglass effect can be mitigated, right? This is part of your task, right? So here is one tutorial questions. You can try it on your own. So any questions so far? Let me check the comment. Okay, no comment, no question so far, only matrix number, all right? Okay. So here, some sayings say that insanity is doing the same thing over and over again and expecting different results, all right? Okay, so we try a different way, okay, of live streamings again and other things, okay. So hopefully that will increase your interest, okay. Then also I recommend you to watch this YouTube, a TED Talk, all right, whenever you are bored, all right. Okay, so no questions, then we will move on, all right, to the next part, all right. So this part will discuss more on the difficulty in the modeling itself and what you can do during the meshing, right? The typical way of doing it, okay, during the meshing, okay. So difficulty in modeling is the phenomena or the process itself is understandable, all right, because it highly depends on the knowledge, okay. If you know more physics phenomena occurs, okay, then it will helps you to model better, okay, on the real conditions, okay. Then this difficulty in modeling will include like choosing the proper type of elements, understanding the type of boundary conditions, as I've mentioned, the physical phenomena occurring or imposed on that particular process or the problem itself, okay. Then also the kind of load, okay, what is the numbers and how you can get all these, where they are acting, okay, the locations, the magnitudes, all these in real, we just apply it, right? So there is load, but in actual, how we get this number, 1 Newton, 10 Newton, 100 Newton, we don't know, right? So we have to have this basic mechanics or fundamentals to help us to actually estimate all this value and how they can be located in the model itself. Okay, that's free body diagrams will helps you to actually locate all these locations. Okay, so when we apply the loads, as we have discussed previously, all the forces or the loads will be applied at the node, not in between the node. Okay, because the FEA itself will not calculate the force acting in between the node, all right, except there is a mid node in between the edge of the element is, right? So most of the commercial code or commercial program, they will usually call it as a commercial code, okay? Because that program behind it is the code. That code is the intellectual property of that software, right? So those codes will give us warnings like overly distorted element shapes, checking for whether there's too much support, no support. Okay, when we apply a force, when we forget to give a support, then the object itself will fly, right? When we do the simulations and so on, right? So all this is up to the users. Okay, that's why all this knowledge will helps you. Okay, the more you learn, okay, and you practice, then you know what kind of difficulties. Okay, so you can always search online. Okay, Google is your very good friend, is my very good friend as well, right? So you just search for the literature to overcome all this difficulty. Okay, so you can search and you will see that for example in ANSYS there is a student community, okay, that's talk about the convergence issues for the highly distorted elements and so on. Okay, so that will helps you, right? So first thing that the software or the commercial codes will do, okay, to help you is they can calculate the aspect ratio. Okay, so this is a very essentials parameter that most of the FEA analyze, okay, will do. Okay, they will check the aspect ratio. Okay, this aspect ratio is actually the ratio of the longest dimensions to the shortest dimensions of a quadrilateral elements. Okay, for examples, we can see that for this diagram itself, the aspect ratio will be 24. Okay, very long and very short on the two edges. All right, then it slowly changed to 6, 3.6, 1.5, 1.1, and so on. Okay, so what we can see that this aspect ratio, in many cases, when it increases, then the accuracy of the solutions, the accuracy of the solutions will decrease. Okay, or the inaccuracy of the solutions will increase. Okay, so the higher it is, the accuracy will decrease, right? So this is the studies, okay, on how the percent error in the displacement itself, okay, actually change, okay, as the aspect ratio decrease. Okay, so when the aspect ratio decrease, then the accuracy actually increase, right? So it's getting nearer to the exact solutions. Okay, so for a Q4 itself, we would like to have a low aspect ratio as well as the corner angle of the quadrilateral near 90 degree. Okay, they can have something like this, okay, when they mesh. Okay, but if possible, as near as 90 degree as possible. Okay, that if unless you are doing the meshing algorithm, then I think you cannot control much. Okay, you can only control several things. Okay, how it looks, you can do a remesh again. Okay, to obtain a good elements. Okay, but how the software do the meshing, is their own algorithm. Okay, that's why there is studies or research on the meshing algorithm as well. Okay, on how to mesh a good one that meet all these conditions, right? So if you want, okay, what we can do is, if let's say you have an object in these shapes, okay, in order to get a proper meshing, okay, let's say you want proper meshing on this side which you have a slanted. So what we can do, you can do a partitions. Okay, you can always do a partitions so that when we mesh, okay, it is always constrained, okay, with our so-called desired angle. All right. So this is how we can do it. Okay, or else the software will run on their own. Okay, this is how we can manually tweak the meshing itself. Okay. So there is exceptions for case where the aspect ratio approaching 50 still produce reasonable or satisfactory results. Okay, this is when that particular elements itself is not subjected to stress gradient. Okay, not much stress actually acting on that. Okay, maybe some part that are extra. Okay, so then it's not relevant. Okay, for example, you have a structure similar to this, okay, and you apply a force on these directions, and this is our so-called fixed support. Okay, so what happens is that this force will be transfer, okay, all the energy will transfer, so the support will be mainly on this particular part. All right, so whatever we do on this side, okay, is less significant. Okay, meaning to say this part, even though it has a bad aspect ratio, is acceptable. Okay. Those poor element shapes in the model will usually result to a poor results. Okay, so then we can see the elements with poor shapes. Okay, very large aspect ratio, almost like a triangle shapes. Already a triangle shape, even though this is a Q4, and also a very large angle, okay, and a very small corner angle. Okay, we try to avoid all these things. Okay, but then we cannot control much. Okay, what we can control, we do a partitions to minimize the number of this kind of bad elements. Okay. You can always use symmetry cases. Okay, because we have, for example, this testing bar itself. Okay, we have fillets and so on. Okay, we can minimize the problem, okay, by doing analyze the where it is symmetry. All right, and this symmetry itself is good somehow to reduce the possibility of the meshing algorithm to mesh as not as what we want. All right, so if you run it, okay, if a good meshing, sometimes it give you a good result, okay, but sometimes it may give you a bad result. That's why I told you to do a partitions. Okay, so when we do a symmetry, it's very similar to doing a partitions. Okay, so when you cut it off, so you are limiting the meshing algorithm to a selected area. Okay, so that it's try to adjust to fit in that particular area itself. Okay, so here again we can see that in this particular transitions of Q4, okay, we can see a Q4. Okay, so the algorithm will start to mesh, and then when it approaching to the end, okay, we try to reduce the number of elements because our stress point is here. Okay, when we want to do a tensile test, this is our area that we want to know, right? So this part is become less important. Okay, but then when we do a meshing itself, we cannot simply connect it directly, okay, to the other Q4. Okay, so what we do, we will include a transitions triangle. Okay, so this transitions triangle will helps us to distribute this load, okay, to the other nodes itself, right? So we can include a transition triangle. Okay, whenever we try to match from a smaller Q4 to a larger Q4 and so on, right? So some software they may not only focus on the Q4, they can do this so-called mixing of triangular elements as well as the quadrilateral elements itself, okay, but on their own, okay. But this is how, if we want to really control it, okay, then this is a better way. So you can see that all the elements are actually arranged or meshed in a very uniform way, okay, so that the behavior becomes more uniform, right? So again, very cautious to be applied, okay? Whenever we apply a symmetry, make sure it's not applied to maybe a vibration cases or buckling modes or so on, because when it buckle, we cannot simulate that particular buckling in a symmetry way, okay? It may buckle in non-symmetry way, okay? So in that case, you cannot use symmetry, okay? So be careful with all these things, all right? How the results, the estimated result of your displacement will actually change. Is the result of the displacement symmetry? If it is, then you can use the symmetry. If not, then you cannot, right? Then we have these natural deviations and the discontinuity. Discontinuity can be any kind from a load, okay? When you suddenly add a load at this, then there is a discontinuity. Then you may want to subdivide them, right, to increase the number of elements over here, right? Then also there is abrupt changes in the distributions, okay? Then you may want to partition this and then add this as one element, right? Other cases will include changes in the plate thickness, okay? Suddenly this plate thickness change, okay? Then we need to include an additional point, okay, to represent that particular changes, okay? So we have to do a subdivisions or partitions in between that, okay, particular point. Also, whenever there is a changes in the material property, yes, we have to cut it clear to represent two different materials, okay? In some cases, there is some support, okay, embedded or implant, okay, inside. So this may be an implant of a bonds, okay, surface, okay. So we can see that we will mesh differently for different material itself, all right? And we also notice that we will always ensure that even though they are meshed, okay, we have to make sure the nodes are continuous, okay, they are actually matched, right? Unless you apply different kind of conditions, okay, it's just like contact type of conditions, then the FEA software will treat them differently, okay? Other than that, if we intend just to do a static or maybe not really dynamics, okay, then this node must be matched together, right? Other natural deviations will be at the re-entrance of corner, our stress concentration part, or maybe at the holes area, right? So you can cut them into a quarter of the plate and simulate them, right? Then also the structure of a distributed load, okay? You may want to naturally add all this meshing, okay, so that we have a proper distribution load actually being represented properly, right? In the refinement methods, okay, in general, we can classify them into three refinement methods, okay? The H, the P, and the R, okay? So these refinement methods, you can apply it by doing your own so-called divisions or partitions, okay? Or in the software itself, they have their own so-called refinements, all right? And the software will use the same terminology, H, P, and R, right? So for the H methods, it's actually to approximate the solution with a larger number of lower lower order elements. Means this is a single order. Okay, this is a linear elements itself. Okay, so what we can do is we increase the number of mesh. Okay, using a larger number. Okay, we can subdivide them into this form, or we can subdivide them into a uniform mesh. Okay, we call this as a H mesh. Okay, refined from the original mesh, right? Then for the P methods is very straightforward. Okay, we know that by increasing the linear functions of the displacement itself, the accuracy will increase. Okay, but then you may have the problem with the memories and other things. Okay, so we can always increase this type. Okay, by increasing the polynomial shape functions of the element itself, right? That is P, the polynomial, right? And the R methods of refinements is when you try to relocate. Okay, we try to relocate. Okay, based on our knowledge, we know that the force is acting towards the end. Okay, so what we do, we try to shift these elements nearer to the load. Okay, this is another way of relocate. Okay, so that this part become less significant. Maybe, okay, we know that maybe this is not significant, then we shift that towards the load, right? This is the R refinement methods. Okay. And then these transition triangles, as I've mentioned previously, we can include a transition triangle in between two different size of elements. Okay, so this is necessary. Okay, because the intermediate node, okay, for the Q itself along the edge are inconsistent and the form with the energy formulations of the CST. Okay, so it's not recommended that we match them to the intermediate nodes. All right, so this way is okay. All right, then for the concentrated load point, yes, we can have a load acting on the one point. What we do, we remesh it. Okay, near to the point, we mesh it with a finer mesh, right? And what happens is that in actual cases, okay, theoretically, if we have one single point load, okay, and this point itself actually acting in a infinitesimal area, this point can penetrate through any kind of object, just like a needle, right? Okay, so what happened is that in the finite element analysis, the infinite displacement and the stress are never compute. Okay, so what we do is that the infinite displacement and the stress can approach only as the mesh around the load is highly refined. Okay, so if we really want to see how the force actually penetrate through an object, what we can do is we refine more meshes, okay, and see how the stress actually change at this particular point and whether it will penetrate through or not. Okay, penetrate through it or not. Okay, so in some case, these stresses near the concentrated force are not the object of the study, right? We can have other ways to model the concentrated load by adding the additional elements. Okay, you can do that, but I would not recommend that. Okay, to add additional load. Okay, because that may increase, especially when you define the material property of your elements. Okay, this material property may behave differently. Okay, when the load itself is transmitted. Okay, then also the stress is predicted at the infinite at the reentrance of point B. Okay, this is a point, right? Not B. Okay, what happens is that in the finite elements, if we are using a linear elastic material model, we will never get convergence. Okay, at this particular point. Okay, because of these sharp edges. Okay, so what we can do is that you can change, okay, by putting a fillet or a fillet, okay, to mitigate this so that there is a transitions, okay, or else it will theoretically calculate as an infinite point itself, okay, or infinite stress acting on that particular point. Okay. If we want to simulate an infinite medium, meaning to say, let's say this is a foundation problem, okay, in the civil engineering. So assuming this is a ground, okay, our ground is infinite, right? So you're stepping on ground. So in order to model this, we have to decide where to cut, okay? So this idea is that we will do it using a try and error procedure, okay? So this procedure itself, we will try to see how far it is, okay? If we have a load acting on this particular point, okay? So how far it is, it will affect, okay? And when the effect is insignificant, then meaning to say we know this length itself is sufficient, okay? Then we can model it to cut it off, right? So in these cases, we will have to run a preliminary test of FEA, okay? No FEA cases, we run it directly, okay? Most of the case, we will model it, okay? Describe what is the parameters acting on it, and then from there we will try to put in our load and see what is the result and how it can be improved, okay? And we will see what happens on this end, okay, whether it's sufficient or not to actually model the whole conditions, okay? Then also when we try to mix different kind of elements, then we have to know the characteristics behind each of these elements, okay, because they have a different degree of freedom at each node, all right? For the beam, the node itself can rotate, right? But then for this Q4 itself, they cannot rotate, they can only translate, okay? They have different behavior. So when we mix them in this particular form, okay, meaning to say this point A is allowed to rotate. So once we put a force, this beam will just go down, okay? We create a mechanisms, okay? So that's why mixing them is, we have to know why, all right? Have to be careful, okay, when we try to mix them. So to solve this problem, what we can do is we extend it into the plane, okay, so that the rotation is here, okay, but then this rotations now is being constrained, okay, since this point is only allowed to move in a displacement form, okay? So in this way, then yes, the moment due to this P is now transferred to our plane elements, right? In the interpretations of the stress, in general, or the common practice, those stress are evaluated at the centroid of the elements, okay? But alternatively, in most of the software itself, we can use an average, and this average is actually the values of the stress evaluated at each node of the elements, all right? So how we evaluate, we can sometimes evaluate it at the Gauss point, okay? We have 4 Gauss points for each of these Q4, right? So we have, let's say we have four Q4 elements, okay, as shown here, okay? So this Gauss point may transfer, or this value, once we compute it, we can transfer or extrapolate it, okay, to the node itself, okay? So we call this averaging methods, okay? Or we can also, when we see 2 elements are actually combining, so this stress value also being put to the same node, right? Remember, this node are a single node itself, okay? So what happens is that this node will do an averaging of the node, okay? We will call it as smoothing, okay? So this is how the software can actually shows you a nice colorful gradients of stress, okay, because they are doing a smoothing between them, okay? But then we have to take into considerations, okay, this kind of smoothing may lead to some kind of error, okay, when we interpret it, okay. This happens when there is a changes in the thickness, okay, or the material stiffness, okay. Meaning to say, if let's say this is a very large element, okay, and this is a very small element, okay, then this point itself, when we average them together, may not represent the real conditions, okay, because this part is larger, then the stress occurs may be lower, okay, and this part is smaller, the stress acting may be larger, but then when we average them, they cancel out each other, okay. That leads to the so-called some kind of error in the result itself, okay. Same thing for the string fit problem, okay. The circumference stress between the matching cylinders are usually quite different, okay. So you have to take care into these connections in between different materials and so on, okay, even though it shows you a very nice results, okay. In general, we will always check the results for consistency, okay. As I've mentioned, first check the displacement characteristics or the displacement result and see whether it's behave as what we intend or not, okay. Then only we will try to check for others consistency. For example, we will check whether the support node really give us a zero displacement or not, okay. A symmetry exists, okay, then it should behave like a symmetry, okay. Then the last part will be when we try to validate our results, okay. Then what we need to do, we have to compare our result with any kind of technique, okay. It can be anything from theoretical part, okay. We can do it from formulas, okay. We can get it from experiments, or we can also do FEA, okay. As I say, we can do a preliminary FEA, get an idea of how it behaves, and try to remesh it and see whether this behavior change, okay. And if it change, why, we have to understand, okay. We will have to compare, okay, so that we can justify, okay, what we present, okay. So here is a tutorial for you, okay. You can try this tutorial in the Lisa FA as well. If you don't have, then maybe you can try other software. If can't, you can skip this, right? This one for those who really don't have a computer, right? So I recommend you to try this, okay. So that's all for this lecture. So any questions?